Okay, I announced that earlier. I'm going to give a, midterm exam on April 5th, right, Tuesday, and then I canceled, this, and this time I think, it's better to cancel this one, and then midterm exam here, so that you have more time to prepare for midterm exam. So shouldn't matter, right? Can you do it this way? Canceled on Tuesday class, and I'll give you a midterm exam on Thursday. Okay? 출정이야? Okay, then forget it. Okay, then sorry. We'll have you will have a midterm exam on Tuesday then. Okay. Okay, in the homework, the first problem, I said a MATLAB code will be given to you, and actually, I'll send the MATLAB code this morning by email, and which was written, by one of the students earlier. Anyway, you can write your own code if you want to, or you can modify the code, or you can just use that code to do first problem. And the other handout is describes the panel method, the detailed panel method that we are going to discuss today. Okay, so that will be useful for you to do your homework. Okay, let's continue to discuss complex potential that I started it on Tuesday. So complex potential is defined as summation as phi plus I psi. Here, this is velocity potential. And this is stream function. Okay. And phi and psi are both of them are functions of z, where z is x plus iy. So this z is defined only on plane. Therefore, this complex potential can be defined only in two-dimensional problem. So to solve three-dimensional problem, this complex potential is not, that useful. But for 2D problem, this is sometimes, this concept is very useful. And so here, since you have a function f, complex potential f, you can find the complex velocity by taking z derivative. Just like when you take x derivative, you will get when you get an x derivative of velocity potential, then you will get a horizontal velocity. When you take y derivative, you get a vertical velocity. So likewise here, if you take a z derivative of f, so if you take a z derivative in this way, then you will get the complex potential. Okay, no, I'm saying complex velocity. And actually, what it means, this is x plus iy. So this means you can take a derivative either in the x direction no. So this means this. what it means, this implies you can take a derivative in any direction. Okay. So they have to be, the same all the time, because this function f, it has a very nice property, which is, analytic, meaning that, this f is all bounded and so on. So when you take an x derivative of f, then you will get d phi dx plus I d psi dx, right? So when you take y derivative with I in the denominator, then I will get d phi I dy, which means minus I d phi dy, and then I have I d psi I dy, so I can cancel I, and then at the end I have this. Okay. So df dz means you can take a derivative in this way or that way, meaning that this expression has to be the same as this expression. Otherwise, I cannot do this. I cannot take a derivative, as I wish. So, which means, if I write this, for this guy to be the same as this guy, real part has to be parts have to be the same, and imaginary parts have to be the same, meaning that d phi dx has to be the same as d psi dy. And the imaginary part gives you d phi dy has to be the same as minus d psi dx, because I have minus sign here. Okay. As you can notice, d phi, by definition, this is a horizontal velocity, and this is also horizontal velocity. When you take a y derivative of a stream function, then that's the definition of u. And when you take y derivative of velocity potential, or when you take a x derivative of stream function with a negative sign, you end up with b. Okay, so now we can show this expression is exactly the same as this expression, and then these are nothing but the definitions of horizontal velocities. So sometimes this relationship between phi and psi are called Cauchy-Riemann. Cauchy-Riemann relationship, or Cauchy-Riemann relation. And the reason why you have some connection between phi and psi is both the velocity potential and stream function satisfy the Laplace equation. Okay, because of that they have some connection. If this comes from this, okay, by definition, Laplacian of stream function is minus minus vorticity, and if this vorticity is not equal to 0, in other words, if the flow is rotational, then there is no connection. First of all, you cannot define velocity potential, okay, for rotational flow. Since this time we are looking at a rotational flow, this vorticity is identically 0, so stream function satisfies the Laplace equation, and therefore there is some connection between phi and psi, and that connection can be seen from this Cauchy-Riemann relationship. Okay. And but anyway, so finally, what we really want is the complex potential, and which is nothing but df dz is equal to u because d phi dx is u, and d psi dy is minus I v. Okay. So this sign is somewhat interesting. Over there, you have plus sign for the definition of complex potential. But when you take a z derivative, you have u minus I v. Okay. So if you want to get the v velocity, then you have to take a z derivative and then find minus imaginary part. So some of examples. For example, if f of z is uz, okay, linear in z, and then this is nothing but u x plus iy. So its real part is ux, and imaginary part is uy. Meaning that this guy is phi, and this guy is a stream function. So this is a velocity potential, and this is a stream function. Okay. So as you can see, this represents, the uniform flow in the x direction. So instead of ux for velocity potential, if you write u times z, then this gives you, complex potential for the uniform stream. The nice thing about, one of the nice things about using complex potential is you can get both velocity potential and the stream function, at the same time. So here, psi equal to uy is a stream function, so you can easily draw a stream function, right? Constant stream you can easily draw streamlines, which can be found by setting, stream function equal to constant. So I said this guy is some constant, and then y equal to constant. That's what it means. So these are the streamlines. Whenever y is constant, then that gives you, the streamlines. Yeah. So this is flow going this way. How do you get the uniform flow in the y direction then? So if I want to represent flow in the y direction whose magnitude is v, then Fz has to be, any idea? I'm going to take a z derivative. So if you look at this, I want something, purely imaginary. So when I take a z derivative, I'll get a constant. That constant has to be imaginary. So I have to put I. And then this, instead of having u plus iv, I have u minus iv. So I should get negative sign there. Then if I do have that, then my df dz is minus iv. Since this represents u minus iv, from here I can see u is identically 0, v is capital V. Okay. So once again, this one gives you minus iv x plus iy. So real part is Vy, which is phi, minus Ivx. So velocity potential is Vy, as we expect, because we are looking at the flow in the y direction. And the stream function is minus Vx, which means, if you fix x, then psi is constant, meaning that streamlines are the lines where x is constant. So these are the streamlines. Okay? So these are the streamlines, which is, psi equal to constant. So by changing constant, you can draw, many, streamlines. Another example is when Fz is equal to right? So you can imagine this is a complex potential for a source or sink, depending on the sign of Q, right? We have log R for velocity potential, so that's what we expect. Question? No. Direction is given by this. When I draw the line, this represents flow direction. This stream function can be -1, -2, -3. Doesn't matter. That doesn't represent the direction. Direction is determined by this. So direction, the vertical velocity is still positive. So I expect direction in this way. The value of psi can be negative or positive. So it doesn't matter. The value of this guy doesn't tell you flow direction. Okay, now we have a complex potential for a source. So this is for source or sink, depending on Q, the sign of Q, okay? And this time, Z is x plus Iy, and I can represent the coordinate by using polar coordinates. So x is r cosine theta plus I r sine theta. Okay, and then this is nothing but r e to the I theta. And therefore, if you put the expression for z here, and then I have q divided by 2 pi log r plus I theta. Okay, and then I have q divided by 2 pi log r plus q over 2 pi theta I here. So this is phi, and this is a psi stream function. Once again, constant theta gives you constant, stream function. So streamline should be like that. Okay. And the flow direction is outward if Q is positive. And then we have a flow direction in this way. What if I have a, instead of real Q, what if I have a, imaginary, strength like this? So here gamma is real. So all I did is to change Q, real, strength, to purely imaginary strength. Okay. Then we can go through exactly the same thing. Okay. And then what we have is so this is a real part and imaginary part. And then I end up with minus gamma over 2 pi theta. And then I have plus I gamma over 2 pi log R. So this is phi. Real part of complex potential is phi. Imaginary part of a complex potential is stream function psi. So what is this? How do streamlines look like? Streamlines are the lines of constant stream function, right? So if this guy is a constant, then you can set this guy equal to constant, then you can draw streamlines, which means the only variable is R, right? So R has to be constant, meaning that streamlines are circles. Okay, so this is the complex potential for a vortex that we discussed last time. So I can draw concentric circles. These are all streamlines. But flow direction, this time UR is 0 because everything is rotating. Fluid velocity vector has to be tangent to the streamlines. Okay, so you cannot have any velocity which is normal to the streamlines. The velocity vector has to be always tangent to the the streamlines. So flow can go either this way or that way. And so UR is 0, U theta is minus 1 over R. Actually, okay. UR is defined 1 over R d phi d theta. So from there, you can see gamma divided by 2 pi R. So this is a negative, meaning that flow is rotating clockwise. Okay, counterclockwise direction is defined positive because we measure angle from 0 to pi over 2, pi 3 pi over 2, and so on. So this means, flow direction is this, clockwise. So if you want to have a flow in this way, then the complex potential should be minus gamma I gamma divided by 2 pi log z. Okay? Then flow direction is counterclockwise. So just by changing the sign from positive to negative, you can generate flow in the counterclockwise direction. But once again, by using complex potential, you can get both velocity potential and stream function at the same time. Also, you can write the stream the complex potential for a dipole. Okay. Like this. So now when you take a z derivative of log z, you get 1 over z. Okay? So once again, this is mu x plus iy. And then I can write this as x squared plus y squared by multiplying x minus iy, multiplying the denominator and numerator by x minus iy. And then I can collect the real part and imaginary part. Okay? Oops. So this is a phi for dipole, and this is for phi psi, stream function psi for dipole. Without I, of course. But in general, mu can be the complex number depending on how you align dipole. If you want to align in the x direction, then mu is real. If you want to align in the y direction, then mu has to be purely imaginary. So this time, this is dipole aligned in this direction. So dipole aligned in this direction, then your f of z has to be I mu z. Okay. So in general, you can have both real and imaginary part. You can generate any multiple by taking z derivative. If you take the derivative of this guy, then you will get a z 1 over z square, and so on. So in general, you can write any multiple in this way. So most general solution is f of z is u minus I v z, which represents the uniform stream in any direction, and then you have q plus q minus I gamma, or plus and minus, it doesn't quite matter. Doesn't matter, but so this represents source and vortex. This is uniform stream, and this is source and vortex, and then you take a derivative, the summation from 1 to infinity. This mu n can, nth power, and mu n can be complex. Okay. So that's the most general solution for two-dimensional flow in terms of a complex potential. So this is similar to what we had before, and it has a little compact form, and also it contains both velocity potential and stream function. So, for example, for flow around a circular cylinder, we can write complex potential f of z as a linear combination of u times z, which is a uniform stream, plus ua square divided by z. So this is a uniform stream. And this is a dipole. So when you add uniform stream and dipole, then we could generate flow field. And when you take a z derivative, you will get a complex potential velocity, which is u minus iv. So in that case, u plus. Okay. So if you take a real and imaginary part, you can get a horizontal velocity and vertical velocity. And from here, you can find the phi plus I psi. So you can check, if when you collect a real part, then you can check, the previous solution that we got. Yeah. Then once you find a stream function, you can draw a stream function that we have before. So it looks like this. So each constant stream function gives you this stream line. Okay, so these are stream lines. And so this circle is a boundary, and the flow direction is this way. And flow direction has to be this way. So you can draw, stream lines from this stream function. Now we can make the problem a little, bit more interesting. What if I add vortex to this problem, but with a negative sign? So this is a uniform flow, a circular cylinder sitting in a uniform flow, and now add the vortex This vortex is a rotational flow. It gives a rotational flow field. So let's think about it. And this vortex generates flow like this, right? Because I have a negative sign. Oh, sorry, I need I. Since I have minus sign, I generate the counter rotating flow in the counter counterclockwise direction. And then originally I have flow like this, and here and here without vortex. Now I add flow like this, and then what happens? Hold on. So I have flow like this. If I have a counterclockwise direction, then I have flow like this. Which I don't want. Let me change the sign. Positive sign, then I will have a clockwise flow. Then this is a flow by dipole and uniform stream. Then I add flow like this, right? Of course, the magnitude doesn't have to be the same. Okay, so then at the end, my flow is bigger here and smaller here. When I add up, this is due to the dipole and uniform stream, and this is due to, the vortex. Okay, and at the end, I have a much bigger fluid speed at the top than bottom. So if I keep increasing, the rotation, the strength of vortex, gamma, and then at some point, this guy will be exactly the same as this guy with the same magnitude, but in the opposite direction. So depending on the flow speed, I could have something like this. So gamma is positive, and then I could have a stagnation point here and here, like this. This is a circular cylinder. When I add rotation, my streamline could look like this instead of that. Okay, because the vortex, the flow direction is this way and this way. So at some point, you have the stagnation point. If I keep increasing, the strength of gamma. If you further increase, the circulation gamma, then what? This stagnation point can move to the bottom. First of all, you have to remember that the velocity here and here, velocities here and here are smaller than velocity here. In terms of magnitude, maximum velocity occurs here in the absence of vortex. So when I keep increasing, the stagnation point, you keep increasing, gamma, stagnation points move from here to here. Do you see that? So gamma equal to 0. I have a circle. And then I have stagnation point here and here. This is my flow. Flow direction is this way and this way. And velocity is 0 here, keeps increasing, and the maximum here, and then decreasing to 0. So flow anywhere other than on the top and bottom, the velocities there are smaller than velocities here or here. Okay? So now I add, circulation in this direction. Gamma I call circulation. When I add, the rotation speed, and then the vortex gives, flow like this, and flow like this. And then if the rotation is 0, then I have a 2 stagnation point here. When I keep adding, the rotation, then stagnation point starts to move downward. Because here, velocity here and here are have the same directions as the velocity is generated by a vortex. But here and here, the flow velocity is this without the vortex, but the velocity field generated by vortex is in this way. Okay. So that's why stagnation point start to move downward, and that happens. And at some point, if you further increase, the gamma, then at one point you will have the streamline like this. So these two stagnation points can meet at one point at the bottom. If I keep increasing, gamma. Okay. So what happens if I add circulation? This is a velocity field, and here my velocity has been increased when I add the vortex. So velocity here is bigger than velocity here. Previously, velocity here is the same as velocity here. Now, when I add the vortex, velocity at the top is greater because they have the same direction. Velocity here is greater than velocity here, and therefore pressure here, which one is bigger, here or here? From Bernoulli equation. Bernoulli equation said 1/2 rho u square for v square plus p for steady case, and I don't have to worry about the gravity this time is 2D, and that has to be constant. So if the velocity increases, pressure has to decrease to make it a constant. So this time by adding vortex, I increase velocity, so I decrease the pressure. On the other hand, here velocity decreases because two velocity directions are opposite, and therefore pressure has been increased. So this time I had the same velocity, therefore I have the same pressure. By adding this vortex, the pressure symmetry has been broken, and the large pressure here, small pressure here, and meaning that the force is acting this way. Okay? So this force is called lift. Okay. So when the body has some rotation, then this body can experience some force. Earlier I said there is a paradox which says that force in an inviscid fluid, force acting on the body in an inviscid fluid is identically zero, right? If the flow is steady, is unbounded, and there is one more condition. In the absence of vortex, the force is zero. But if you have vortex, then there is a force which we call lift, because the flow is coming this way, and the force is perpendicular to the flow direction. That's why we have airplane and so on, right? So. So, typically this vortex in real world can be generated by rotating, this cylinder. If you rotate this cylinder, if there is no viscosity, what happens? If I just rotate in a cylinder, if it is inviscid, then nothing happens, okay? Because there is no friction between this surface and the fluid, and therefore nothing happens. But if you have viscosity, then because of this guy is moving, there is because of no slip boundary condition, there is some velocity here, and then decay as you move far away from the circular cylinder. So imagine circular cylinder is moving, and then if you're next to the circular cylinder, then you feel the rotation of circular cylinder. But if you're far away from circular cylinder, you wouldn't feel anything, so it has to decay to zero. So it's like 1 over z or 1 over r. As r goes to infinity, velocity goes to zero. So of course this flow due to the vortex is generated by viscosity. Okay. Then we are saying that the viscous effect can be negligible after generating vortex, if the flow remains to be high Reynolds number. So that's a justification of adding vortex to the inviscid flow. Okay. So when you rotate circular cylinder, because of viscosity, you generate some flow velocity field, which can be represented by this rotational vortex. And after that, the viscous effect can be negligible. After the generation of this vortex. Okay. And that kind of argument can be justified when we compare the flow or pressure with the experiment, and that has been confirmed. Okay. As long as your Reynolds number is large, in other words, Reynolds number is defined UL divided by mu. So when you have a uniform stream, and L is a dimension of a circular cylinder, and if this guy is larger than 1, then viscosity effect is viscosity just generates the flow field that can be represented by vortex, and then that's it. Okay. So my favorite example of that is golf ball, right? Golf ball flies because we hit the ball with an angle. Okay, that makes golf ball rotate, and that generates vortex flow, induced by vortex, and that makes this golf ball flat. As rotation increases, the asymmetry increases. So if you hit harder, the ball, flies, higher. That's why when Tiger Woods was good, he's not good anymore. But when he was good, his speed was much faster than his swing speed is much faster than others. Which means his rotation is higher. That's why his ball is always higher than anyone else. Okay, and so that's one of the example. And in the airplane, if you look at the cross section, not this way. So flow is going this way. So you have a cross section like this, right? And then around this, body, you always generate, the vortex. The reason is, there is a separation coming from here because of the angle, and flow cannot go around. You need an infinite velocity to go around, which I haven't talked about yet. But anyway, so to avoid that, in reality, what happens is, you see, shedding like this. And this guy has some circulation or some vorticity. And for your rotational flow, or if your Reynolds number is high, the vorticity cannot be generated. If it starts from 0, it has to be 0 all the time. So to compensate this circulation, this part, and this guy generates vortex like this around the body, and that makes this guy goes up. Okay, so if this guy is gamma and this guy has to be minus gamma, and then what you see is the effect of this vortex. That makes this airplane fly. So the point is, whenever you have circulation around the body, or gamma, or if you have a vortex flow, you have a flow which is similar to the flow generated by vortex, then the body experiences some force which is perpendicular to the flow, incoming flow. Okay. Here, you can see the flow due to the body itself. It goes like this. When you add the circulation, then the velocity field due to the circulation is this way. So here velocity increases and here velocity decreases, and then pressure decreases here, increases here. So that's why you have a flow like that. The force in the z direction. Or you can think this as a rudder. Then that rudder gives you the side force, so that the ship can rotate. Okay, so without this vortex, you have a very symmetric flow like this, and therefore there's no force acting on the body. But as soon as you add in a vortex, then the body can experience force, which we call lift. Anyway, so all those things can be explained easily by using complex potential. And also another useful Another time when this complex potential is useful is when we have a very complex body geometry. So for example, if you have some body geometry like this, if you want to know the flow around this complex body geometry, if you use the complex variable theory, then which I'm not going to talk about, but you can map. So there is some function between, so this is z x plus iy. This is a physical plane. Okay? So this is a real shape in the physical plane. And so sometimes, I can find a mapping going from z to a zeta plane. So this is zeta plane, c plus I eta. And this is a mathematical plane. So using some conformal, so this is conformal mapping, conformal. So basically, you have some transformation function, then you can map this complex geometry to a very simple geometry like a circle in zeta plane. Okay, this is c or psi. This is psi. And so if you know this transformation, then you can easily map this complex geometry to a simple geometry. Then in this plane you can solve it. You know the solution here. Okay, because you have a uniform stream and dipole, then you can represent this solution. You can solve this problem in zeta plane. But what you are really interested in the problem in the z plane. But since you know the relationship between zeta and z, then substitute that into the solution written in terms of zeta, then you can find the physical solution. This can be done only through complex potential. Okay. So sometimes nowadays it's not that popular, but in old days this kind of the trick has been used quite a bit. But finding this transformation is not always easy. Okay. But once you can find numerically or sometimes analytically. For example, ellipse. Ellipse can be mapped to circle easily. There is a analytic transformation between two geometries, and then you can write the solution in zeta plane using uniform stream plus dipole, and then you go back to write the solution in physical plane by using this mapping function, and then that's it. Okay, so to use this kind of a trick, we often use complex potential, but I'm not going to go through the details. And if I want to do it, then I have to say what the conformal mapping is and how to find that and so on. So that might be a little complicated for you. Anyway, so okay. Another problem, another method to solve the Laplace equation for a body in a uniform flow is panel method. Okay. So first of all, if geometry is very simple, like a circle, we know how to solve it. If the geometry is a little bit complicated, then one thing that you can do is you use multiple expansion. So we wrote the general solution, right? And then you determine all the the coefficients of multiples by imposing body boundary conditions. Okay, and that's the second way. The third way is if the flow is symmetric, then as you did in the homework, you can use the distribution of sources singularities along the axis. That's another way. And also this is an alternative way. If you know the mapping between these two geometry, then you can use that. But each has some weakness, and this panel method is the most general method to solve flow around rigid body. Okay, can be used for non-symmetric flow and everything. Also, this method can be used for unsteady problem, as you can see later. Okay, so the idea is very simple. You write the velocity potential as a summation. As a distribution of sources along the body geometry or body surface. So dl is this. And sigma is the strength of a source. Or okay, let me change the notation to be consistent with my handout. Sorry, let me use Q here. Okay. So x is a point in here, and x prime is sitting on the surface of a body. So you have a continuous distribution of source along this body, okay? And x can be anything here, or it can be on this surface of the body. So we represent the solution, which depends on x, in this way. So why is it a solution of Laplace equation? When we take take Laplacian of phi, which is for with respect to x, not x prime, okay? Because this guy depends on only x. X prime is a dummy variable for integration. And when you do that, then this Laplacian doesn't affect this, because it depends on only x prime. And then we have okay, and this guy we know is equal to 0 unless x equal to x prime. Okay. So this guy is equal to 0. So this representation is really solution of the Laplace equation. And therefore now we have a representation here, and this time I want to know what the Q is. To do that, I have to impose body boundary condition. Okay. And in this case, so I can write velocity potential for this problem as ux, for example, if I have a uniform stream, and then I have a phi, And phi, the effect of body, can be represented by distribution of sources. And then I add, the uniform stream. And then my boundary condition is d phi dn has to be 0. Okay, because this guy is stationary. And this gives you d phi dn. Normal derivative of small phi is given by minus u and x. And x is x component of normal vector. So where n is nx and y. Okay? So by imposing this boundary condition, we can find Q. But when you do that, we have to be a little careful. So when I take n derivative, I have 1 over d dn 1/2 qx prime of x minus x prime dl x prime. That has to be minus u and x. Of course, the nx depends on the geometry of body, and n is defined inward normal, like this. Okay. So this is nothing but n dot gradient, and this is gradient with respect to x. Okay. So when this guy goes only here, and so along this body surface, let's put S of B here to represent body surface, and therefore we have 1 over 2 pi let me call this dl prime. I just want to put prime to emphasize that this is an integration over x prime along the body surface, not for x. And that has to be equal to minus u and x on body surface. Okay. So that's a body boundary condition. Now, so here in this representation, x can be anywhere outside of this body. Now x has to be on the surface because we are imposing boundary condition. X prime is a dummy variable. That's the integration. We are integrating over this surface. Therefore, this doesn't matter. But when you take a normal derivative and the imposing body boundary condition, x now is on body surface. Okay, meaning that x can be the same as x prime. If your x is here, x prime is everywhere. So for some x prime, x and x prime are identical. And then what happens? When you take a derivative of this guy, it looks like a 1 over r, and it blows up. Okay, so you have to be careful about this, and so that's what we are going to do. So this integral, the left-hand side, can be decomposed into two. One is, let me put in a bar here. Okay? So bar, with the integration with bar, I'm integrating over everywhere else. Okay? But I exclude, the neighborhood of x. Because, that's why I have a singularity. If my x prime is here, I'm okay, because it doesn't blow up. This guy becomes singular when x is equal to x prime. X prime can be anything when you fix x. Okay? So when x prime is close to x, then I'm in trouble. So I exclude that first, and then I integrate over other contour, and that's what I have this bar. Okay? And then I have to add this area, which I call S epsilon. Okay, so this is SB, but this is S epsilon. Okay, so this neighborhood. And then I have QX prime DDN DL. So you can easily integrate this, but you cannot. So you have to give some meaning of this integration. So to do that, what I do is I deform this the integration path like this. Okay. So what you're looking at is, if I zoomed in like this, and I use a local coordinate. So this is x. X prime is everywhere else. I cannot integrate through this x, because then the code blows. The integral doesn't exist. So what I do is I make a little detour, and whose radius is epsilon. Okay, then I'll make epsilon as small as possible. So this part, let me call it star, and we do the integration for this path, and then I have from 2 pi to pi. Okay, I'm integrating counterclockwise, so I'm going this way. I'm going counterclockwise, and I'm going from 2 pi to pi because I'm going this way, and then I have a q x prime. But q, once again, as we did the last time, x prime and x are so close, and also I can make it as close as possible. Therefore, I can pull out this guy outside like this, and then ddn, normal vector is this way, is nothing but ddr here, because this is normal direction, and radial direction is also in this way. So I can replace ddn by ddr, and then this log is nothing but log r. And then I have to integrate over this path, which gives you r d theta. Okay, because this segment is nothing but r d theta. And then I end up with the q of x. I forgot 2 pi. I had 2 pi here. And then I have 1 over r and r. They cancel each other. And then I end up with a pi minus 2 pi. And therefore, I have minus q of x divided by 2. Okay? So once again, here, what I did is, instead of going through, point x, because which is then I cannot define this integral. So what I did is I just make a detour like this, and with a small epsilon, and then x prime and x are so small, when I can do the Taylor expansion as we did before, and then the leading order term is nothing but q of x instead of q of x prime, and then I integrate over here, and along this, the contour, ddn is nothing but ddr, radial direction. R is measured in this way, okay? And then ddn is ddr, and this guy is nothing but the distance between x and x prime, which is r, and r d theta. Then at the end you have this, okay? So this term gives you minus qx divided by 2 plus 1 over 2 pi integration of q of x prime ddn log x minus x prime dl prime is equal to minus u and x. Okay? So this is the equation that you have to solve for Q. Once you know Q, then you know the velocity potential everywhere. From here, then you can compute, the pressure and velocity and everything. So you have to know this meaning of this guy, okay, which is SB minus S epsilon. So I just cut in a little small area from my integration path. And also, this unknown is Q, which is the strength of a source. Now, Q of x is inside of an integral. So this is an integral equation. And this is along the body surface. Okay. So because the unknown appears inside of an integral, so this equation is called the integral equation. And then, of course, for arbitrary geometry, you cannot solve this numerically. So you have to solve, you cannot solve analytically, so you have to solve numerically. And that's what the panel method is. Okay, unfortunately, I don't have time. I spent too much time on the complex potential today. So I'll continue to discuss this, on Tuesday. So I'm not so sure if you can start, the problem 1 this week, although I don't expect anyone to do homework this weekend. But you try to read, the handout on panel method if you want to. Otherwise, you can hold it till next Tuesday. Probably I can extend the due date. Okay. Because I haven't finished it as far as I want. I was in a hurry to finish it, but I don't have much time. So I'll stop here, and then I'll continue to discuss panel method on Tuesday.